Alright, welcome back to linear algebra. I want to do a new approach to linear algebra today. So far we've been working through page by page, section by section. We're almost done with chapter 1, but it's taken, 3 months to get here? And so I think, I can continue doing this, and it will take me, I don't know, a total of, I don't know how many days that would be, like 1,000, 3 years, page by page like this. But I have a suspicion that there's a faster way to do it, and I've already determined a pretty quick way to learn other things, and might as well try it out on linear algebra a little bit, and we can always go back to the original method or interleave it and mix it up a little bit. But what am I talking about? Newer method. 80-20 quizzes, starting zoomed out really far first, and then zooming in further and further as I want to get more granular. And I think if I do these quizzes before the actual section, I can actually read faster because I won't be so caught up on every little word. I'll know already what the general ideas are. So let's just say elementary linear algebra by Anton and Call. And this is elementary algebra. Anton and Call is a foundational text focused on core ideas of vectors, matrices, linear transformations, eigenvalues, and vector spaces. The 80-20 concepts that explain most of linear algebra's applications. Before we begin, can you clarify what kind of focus you'd like for the quiz? There are 3 possible directions: conceptual mastery, understanding the ideas, what linear independence means, why eigenvalues matter, etc. Computational practice, testing skills, computing determinants, solving systems. Mixed approach, a blend of conceptual and computational insight, like what most courses test. I guess both. Everything, but we won't be able to solve a lot of it. We'll do a comprehensive everything quiz covering both conceptual understanding and computational reasoning, and centered on the 80-20 ideas from Anton and Call's elementary linear algebra. We'll go through roughly 10 to 12 questions, each focused on a key insight that drives much of linear algebra's power and structure. A system of linear equations has more unique unknowns than equations. A system of linear equations has more unknowns than equations. Which of the following statements is most likely to be true? The system has no solution. The system has exactly one solution. The system has infinitely many solutions. That one. Yes. When a system has more unknowns than equations, it's said to be undetermined or underdetermined. Such systems usually have infinitely many solutions because there aren't enough constraints to fix unique values for all variables. However, it's possible, though not typical for such a system, to be inconsistent if equations contradict, but many have infinitely many solutions, captures the most general truth. Which of the following statements best describes linear independence? A set of vectors, I don't know what linear independence is. A set of vectors is linearly independent if no vector in this set can be written as a combination of the others. Set of vectors is linear independent, so it's all about set of vectors, if no vector in the set can be written as a combination of others. If a set of vectors is linearly independent if their magnitudes are all different. A set of vectors is linearly independent if the dot products are 0, if the sum equals 0. I'm going to say a set of vectors is linearly independent if no vector in the set can be written as a combination of the others. Linear independence means that no vector in the set can be expressed as a linear combination of the others. The only solution to That equation is when all coefficients ci equals 0. No vector in the set can be expressed as a linear combination of the others. The only solution to is when all coefficients. This concept is central because it defines a basis which is the minimal, non-redundant set of vectors that spans a space, one of the 80-20 foundations of linear algebra. If A is an n by n matrix and determinant A equals 0, what can we conclude? It is invertible, it is singular, it is, A represents a one-to-one transformation. A has linearly independent columns. A is singular, or yeah. Correct, that's good. I'm like 2 for 3 right now. If determinant A equals 0, the matrix A is singular, meaning it has no inverse. This also implies that its columns are linearly dependent, and the associated linear transformation compresses space. It reduces dimension, for instance, mapping a plane into a line. The determinant acts as a measure of how much a transformation scales volume. A zero determinant means it collapses volume entirely. Which of the following best describes the geometric meaning of an eigenvector? A vector whose length changes but direction reverses under a transformation. I don't know what an eigenvector is. A vector that remains unchanged in both direction and magnitude under a transformation. A vector whose direction is preserved, possibly flipped, when a linear transformation is applied. I'm going to go for that. An eigenvector of matrix A is a non-zero vector whose direction is preserved. It may be flipped or scaled when transformed by A. The scalar lambda is the eigenvalue. This is A, matrix A times V equals lambda V. Scalar V is the eigenvalue, representing how much the vector is stretched or compressed. This captures the deep geometric insight that linear transformations have preferred directions, that axes along which they simply scale space rather than mix it. If two matrices A and B are invertible, which statement is always true? If they're invertible, okay, I can get this one. A plus B, the inverse of A plus B, the sum of A plus B equals inverse of A plus inverse of B. The product of the inverse, or the inverse of the product AB equals the inverse of A times the inverse of B. The product, or the inverse of the product equals inverse of the product A times B equals inverse of B times inverse of A, and then the inverse of the difference between A and B is inverse of B minus inverse of A. Well, I don't remember ever reading about a difference. I think it's C. It's the product. The inverse of the product is equal to the inverse of the component matrices, but in reverse order. That's if it's invertible. All right, for invertible matrices A and B, that's right. The order reverses because matrix multiplication is non-commutative. The operation depends on order. This property reflects how composition of linear transformations work. Applying A, then B is undone by first undoing B, then A. Which of the following best characterizes a vector space? Okay, any set of vectors that can be added and scaled while remaining within the set. don't think so. A collection of points in space that have integer coordinates, definitely not. A set of linearly independent vectors, set containing only zero. I guess it's got to be a set of vectors that can be added and scaled while remaining within the set. A vector space is any set of vectors that is closed under addition and scalar multiplication, meaning that adding two vectors or scaling one by a real number still produces a vector in the same set. This closure property is what allows vector spaces to support linear combinations, linear transformations, and basis representations, the structural backbone of all linear algebra. Hold on. Before we continue, is r to the n, is that what a vector space is? Is that a vector space? Yeah, okay, that is a vector space. Must satisfy 10 axioms, but the essence is simpler. A set of objects forms a vector space if you can add them and scale them by real numbers and the results stay within the same set. Wouldn't that mean the set is infinite? Yeah, infinitely many vectors. Isn't a vector space all of the possible real vectors of that degree? Core idea: vector is one specific element of a vector space. Oh shoot, I meant to say. All right, bro, I do understand that shit. Boom. What does the rank of a matrix represent? The number of zero rows in its reduced row echelon form. The number of linearly independent columns or rows. Sum all the diagonal elements. The number of pivot values minus free variables. I don't know. Number of linearly independent columns or rows. Boom. The rank of a matrix is the number of linearly independent columns or equivalent rows. It tells you the dimension of the column space, the subspace spanned by the matrix columns. Intuitively, rank measures how much information or dimensionality the transformation preserves. For example, a 3x3 matrix in a rank with rank 2 compresses 3D space into a 2D plane, losing 1 degree of freedom. In the equation ax equals b, a unique solution exists if and only if A has linearly dependent columns, A is singular, A has a full rank, the determinant of A equals 0, no. A is singular, no. Actually the opposite. It's not B or D, it has to be invertible. A has linearly dependent columns. A has full rank. I don't know. Linearly dependent columns. No, it's full rank. A unique solution to AX equals B exists only when the matrix A has full rank, meaning all its columns are linearly independent. If the columns are dependent, your choice A, then there are infinitely many solutions, if consistent, or none, if inconsistent. Full rank ensures that the transformation represented by A is 1-to-1 and onto. So each B corresponds to exactly 1x. Which of the following statements about orthogonal vectors is true? Their magnitudes must be equal. I don't know what orthogonal vectors are. They are always linearly independent. Nope. Their dot product equals 0. Two vectors are orthogonal if and only if their dot product is 0. U times V equals 0. This means they are perpendicular. They share no component in each other's direction. Orthogonal vectors are actually linearly independent unless one is the 0 vector. So option C is the opposite of what's true. Did they say dependent? Oh, there's a linearly independent and linearly dependent. Orthogonality is foundational because it makes vector spaces easier to work with, simplifying projections, decompositions, and computations like Gram-Schmidt process. If Q is an orthogonal matrix, which statement is true? The transpose of Q equals the inverse of Q. The transpose of Q times Q equals 0. The determinant of Q equals 0. The columns of Q are linearly dependent. I have no idea. Transpose of Q times Q is 0. There's almost no chance that that's right. Yeah. A. The transpose of Q is the inverse of Q. For n orthogonal matrix Q, the columns and rows form an orthonormal set, meaning they're mutually perpendicular and each has length 1. This property ensures that the transpose of Q times Q equals I, and therefore the inverse of Q equals T, or transpose Q. So while your choice B was close, it isn't 0. It's actually the identity matrix, which preserves lengths and angles under transformations. The eigenvalues of a triangular matrix, upper or lower, are the entire first row, last column, main diagonal, or the entries. The eigenvalues of triangular matrices, upper or lower, are, I don't know, the products of the diagonal elements. No, C, the entries of the main diagonal. For any triangular matrix, upper or lower, the eigenvalues are exactly the diagonal entries. That's because the determinant of A minus lambda I, which defines the characteristic equation, simplifies to the product of the diagonal term minus lambda, making each diagonal element an eigenvalue. So while the product of the diagonal entries, your choice D, gives the determinant, the entries themselves give the eigenvalues. All right, final question, 12. Which of the following statements about the null space of a matrix is true? It contains all vectors x for which ax equals b, contains all vectors x for which ax equals 0, contains all the column vectors a is always equal to the row space of a. It contains all vectors x for which ax equals 0. Let's say that. Yeah. All right. The null space or kernel of a matrix A is the set of all vectors such that ax equals 0. It represents all the solutions to the homogeneous system, and it tells us which inputs the linear transformation collapses to 0. Its dimension is called the nullity, and together with the matrix rank, It satisfies the fundamental rank nullity theorem. Rank A plus nullity A equals number of columns of A. All right. Wow. All right. Here are the core ideas that explain most of linear algebra. Systems of equations equals matrix transformations. Every linear system corresponds to a matrix acting on a vector. Linear independence defines structure. It tells you whether columns bring new directions or repeat existing ones. Determinant signals invertibility. 0 means the transformation collapses dimension. Rank measures information, how many independent directions a matrix preserves. Null space captures loss. All inputs mapped to 0. Eigenvalues and eigenvectors reveal fundamental modes of transformation, stretching, compressing, flipping along preferred directions. Orthogonality simplifies everything, making spaces easier to navigate, measure, and project onto. Vector spaces generalize these ideas. Any structure closed under addition and scaling behaves like R to the n. Master these and you'll understand 80% of what drives all of linear algebra, from solving equations to machine learning and quantum mechanics. All right. On that note, let's jump back into Anki. All right, we got flashcards to do. What must be true for the product of two symmetric matrices to be symmetric? They must commute. Must the product of a lower triangular matrix, must the product of lower triangular matrices be lower triangular? Yes. Must the product of upper triangular matrices be upper triangular? Yes. What is the linear combination of matrices? A linear combination of matrices is essentially I thought I canceled that timer. It's basically a bunch of additions, right? No, yeah, a bunch of additions of basically it's an expression in the form of C1 V1 plus C2 V2 plus C3 V3 plus dot 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 plus Cn Vn, where C is a scalar and V is a matrix. I guess say A. Expression in the form of where CR scalars and A through AR are matrices of the same size. I would say pretty good. I just forgot of the same size. What is a symmetric matrix? A symmetric matrix is a matrix in which the transpose of the matrix equals the transpose, or equals the matrix itself. Square matrix, but the other part was true. Must the inverse of an invertible triangular matrix be triangular? Yes. If A equals A sub ij is a symmetric matrix, what is the relationship between Aij and Aj? Are they the same? They're equal. All right, I'm gonna save the last two for tomorrow, because I want to recall quickly. Yesterday, what we read out of the textbook was basically a theorem for matrix transformations. Some theorems. Basically, the transpose of a zero matrix equal to 0. The transpose of a product of matrices equals the transformation. Matrix transformation of 0 equals 0. Additivity theorem, I believe, or additivity property is that the transformation of a product of matrices equals transformation of A plus transformation of B. Same for division. No, their matrix division isn't defined. There was two others. I don't know. Oh, okay. We got the first one. We got the additivity. No, we did not get the additivity. It's not the product. It's the. Okay, we already into. All right. It was actually the sum of two vectors. The transformation of the sum of two vectors equals transformation of the first vector plus the transformation of the second vector. The difference of two vectors, the transformation of the difference between two vectors is equal to the transformation of the first minus the transformation of the second vector. And then homogeneity property. This is homogeneity property. This is essentially the transformation of a product, a scalar product, like a scalar times a vector is going to be equal to that scalar times the transformation of the vector. Okay. That's it for today. Talk to you tomorrow. See you.